Here we're going to test for linear correlation. I have the times of 28 students and how long it took them to take an exam, and the exam grades out of 100 of those 28 students. We're going to test for a linear correlation between time it takes to do a test and exam grade. The null hypothesis is that the correlation coefficient is equal to 0, that there is no correlation. The alternative hypothesis is that there is a correlation, that the correlation is not equal to 0. Now we're going to insert a scatter plot. So we go up to Insert, Scatterplot after we've selected all of the data like I have, and Excel will automatically create a scatter plot for you. One thing you'll notice about the scatter plot is that all the points are congregated in one area. It doesn't make for a very visually pleasing scatter plot, nor is it very helpful. We could probably cut some data points off of the x-axis here. So we're going to format the axis by right-clicking on the axis, and we're going to change it from a minimum of 20 to a maximum of 100. We'll do the same to the y-axis. We click with the left mouse, then we right-click so we can format the axis. I'm going to change it from 65 to 100. Now we have a scatter plot that's a little more spread out and a little bit easier to evaluate. We can see that there may be a slight negative correlation here. If you can kind of use your imagination to draw a trend line through the points, it may have a slight negative correlation, but in general there doesn't seem to be a relationship between the x-axis and y-axis here. In other words, the points don't seem to create a line. We now need to run a hypothesis test to see if there is a linear correlation. That is, to see if the true correlation coefficient rho, the thing that looks like a p, is not equal to 0. Now we need to calculate the correlation coefficient, r. To do this in Excel, you have to press the equals button, Correl, C-O-R-R-E-L, parenthesis, and now you're going to enter all of the data from column A, comma, all of the data from column B. When you press enter, you will now get the linear correlation coefficient R. Negative 0.154 is not a strong correlation coefficient. A correlation coefficient of a -1 is a very strong negative correlation. A correlation coefficient of +1 is a very strong positive correlation. In this case, negative 0.154 is much closer to 0 than it is to either -1 or +1, and this represents a weak or non-existent correlation. Now we're going to calculate the test statistic to see if it's a statistically significant correlation. We go equals into an open cell in Excel. We're going to enter the correlation coefficient R times the square root of the sample size minus 2, which is 26 in this case, divided by the square root of 1 minus the correlation coefficient squared, or 1 minus cell E6 squared. Press enter, and this is our test statistic with a t distribution. Our intuition should tell us that a test statistic with a t distribution that is only about 0.8 units from 0 is not statistically significant. That is, we should not be able to reject the null hypothesis. To calculate the p-value, use the t-dist function. Your first input is the positive version of your test statistic, so you need to use the ABS absolute value function of the test statistic. Close your parentheses, comma. Degrees of freedom here are 26. That's the sample size minus 2. And this is a two-tailed test. If you look at the alternative hypothesis here, we're doing a two-tailed test. Now when you press enter, you see that the p-value is 43.35%. In step 4, we cannot reject the null hypothesis because the p-value is too high. And in step 5, we arrive at the conclusion that there is insufficient evidence to suggest a relationship between the time it takes a student to complete his test and the score he gets on his test.